adhere to their timings. So starting with the talk by the Department of Physiology, Lieutenant Colonel Vineet Kumar will present a very important and interesting physiologic topic on the heart rate recovery after exertion, which is mainly controlled by an interplay of central inputs, mechanoreceptors, and baroreflex mechanisms. So their team has developed a mathematical model which explains the role and the extent of different regulations in the heart rate control during the recovery period. So now I request Lieutenant Colonel Vineet Kumar to please come on the stage and start the proceeding.
Thank you, sir. So today I am presenting a mathematical model for heart rate recovery after exercise. So mathematics is a language which helps humans understand nature, and mathematical models have helps us in having a relatively objective and accurate understanding of various natural systems. So today we have proposed a mathematical model to understand the recovery of heart rate after maximal exercise. Now, as you could see in the graph, the after exercise, the earlier part of recovery is guided by fast and guided by parasympathetic reactivation, while the later part of recovery is slow and guided by sympathetic withdrawal. Based upon this recovery curve, various HRR indices have been proposed, like HR recovery 1 at 1 minute, 2 minute, 3 minute, etc. The values of this are associated with the reduced value of HR recovery is associated with increased mortality and autonomic dysfunctions. So aim of our study was to have an objective understanding of post-exercise heart rate recovery, while the objective was to derive a mathematical equation catering for the influence of major controllers of heart rate and compare the actual graph with the derived graph. So in first part, we proposed a mathematical model. In second part, we analyzed retrospectively data of 25 subjects. So in long term, heart rate recovery is controlled by influenced by endurance training, gender, age, and individual factors. Short term, there are 4 major regulated controllers of heart rate: the cortical input or central input, the mechanoreceptors, metaboreceptors, and baroreflex system. The central command oblique cortical input, mechanoreceptors, and metaboreceptors influence both the blood pressure and the baroreflex set point. When their output increases, the blood pressure and the set point increases. When the output reduces, both the factors reduces. The set point is located inside the baroreflex system. The baroreflex system detects the blood pressure and compares it with the set point and tries to bring it closer to the set point. The heart rate parallels the blood pressure. So at the onset of recovery, the cortical input falls abruptly and then plateaus, as you could see in the graph, which is a model representative. Similarly, the mechanoreceptors, their output also falls abruptly and then plateaus. On the other hand, metaboreceptors show an exponential decay pattern over time. So you could see the factor e raised to the power minus k3t by I represents the exponential decay, while the representation in bracket represents the efflux of metabolites away from the metaboreceptors. Baroreflex is a negative feedback system. It detects the blood pressure and tries to bring it to its set point. So we have proposed that the baroreflex responds to difference between the blood pressure and its set point. The rate of change of blood pressure, that is the first order differential equation, and the rate of change of and the acceleration of blood pressure, that is the second order differential equation. There might be higher order differential equations detecting higher rates, but we have neglected them for the ease of solving the equation. So these are model graphs representing the effect of the 3 factors. That is, first graph represents the effect of a model graph. It represents the effect of the output with respect to blood pressure, difference between blood pressure and its set point. The second graph represents the first order differential equation, and the second graph represents the model representative of, that is the sinusoidal variation, represents the second order effect of second order differential equation. After catering for the effect of these major controllers, we solved the equation and reached the expression in last line, that is alpha plus beta e raised to the power minus delta t plus gamma e raised to the power minus phi t into cos omega t. The e here is exponential, stands for exponential. We will elaborate upon alpha, beta, etc. later during the discussion part. After this, the parameters alpha, beta, gamma, delta, phi, and omega were calculated for each individual. Then the curves were derived and compared with the actual curve. The Pearson's correlation between the actual and derived curve was 0.952. The reliability and agreement were checked with intra-class correlation, error range, and Bland-Altman plot. The intra-class correlation, the Cronbach's alpha were the same, was 0.938, which shows high degree of reliability. For agreement, the mean of difference was between minus 7.9 to 5.8, and the error range varied between 4.34 to 16.109, which doesn't show very high degree of agreement, neither very low degree of agreement. It is basically a moderate degree of agreement. So the blue curve here in this figure, the blue curve represents the derived values, derived curve, while the red curve represents the actual curve. So you could see that they are pretty much overlapping. These are the same thing, but for all the 24 individual subjects separately. As you could see, the derived curve and the actual curve are almost similar in characters. Since the agreement was not very high, so we checked for any biases, and we found that there was bias, significant bias in 21 subjects. 17 subjects shows deviation of actual and the derived curve at the later part of recovery, while 4 subjects shows that this deviation during the initial part of recovery. So now we'll elaborate upon the various parameters. The alpha basically practically represents the resting heart rate, and it is outcome of intrinsic heart rate and its interaction with cortical input mechanoreceptors and metaboreceptors during resting stage. The beta along with delta is output of metaboreceptors activity, and it predominantly controls the later part of heart rate recovery. As we have already seen, the later part of heart rate recovery is mainly guided by sympathetic withdrawal. So from this, we inferred that the metaboreceptors have predominantly sympathetic influence over sympathetic component. There is evidence for literature in the same. Gamma along with phi is output of baroreflex system. It controls mainly the earlier part of heart rate recovery. Since we have already said there is already evidence that earlier part of heart rate recovery is guided mainly by parasympathetic reactivation. From this, we may have inferred that baroreflex has more stronger control over parasympathetic system compared to the sympathetic system. Omega is totally because of internal working mechanism of baroreflex system, and it causes sinusoidal variations during the heart rate recovery curve. The frequency omega for 25 subjects varied between 0.003 to 0.001, which represents the ultra low frequency part of component of heart rate variability. So the findings of our study was the heart rate recovery follows a bi-exponential decay pattern. One of the exponential decay is because of baroreflex system. Another one is because of metaboreflex system. Baroreflex system also adds a sinusoidal part to it. The baroreflex system is predominantly parasympathetic in nature, and it controls the early part of recovery, while metaboreflex controls the later part of recovery and predominantly sympathetic in nature. Baroreflex system might also contribute to ultra-low frequency component of HRV, which is very less understood. In summary, heart rate recovery after maximal exercise follows a bi-exponential decay pattern, where early part of recovery is dominated by baroreflex system, while later part of recovery is guided mainly by metaboreceptor system. So with this, I end my presentation. And
so thank you, Colonel Vineet, for that interesting mathematical model, and use terms which I don't think that many of us understood what happened, but developing one that shows your competence in this field. So I congratulate you for that same. Now I open the house for question. Yeah, Colonel Koshi and Arnab Ghosh.
You see, the heart rate variability is a very thing I think most of us are interested in, especially those into some form of sports or otherwise. So my question is, when these 21 people whom you have analyzed, most of us are having heart rate variability monitors on our wrists. And these 21 people, what was the exercise that you subjected them to? And, was it an endurance exercise? What was the period after which you undertook when did you measure the heart rate recovery? Because I kind of believe that, if you do an endurance run, then your heart rate variability actually improves. But if you do just a 100-meter dash and then look at heart rate variability, it actually is lower.
Sir, the model, first of all, doesn't analyze heart rate variability. It is just a coincident finding that one of the frequencies, omega, coincides with the range of ultra low frequency range of heart rate variability. Vis-a-vis exercise is concerned, although it was a retrospective data analysis, but it was the data was taken from another study where the subjects underwent maximal exercise, that is a step-up exercise till 85% of HR max. And after that, the recovery was observed till they reached resting heart levels. So in some subjects, it took 1.5 hours, in some 2 hours, 3 hours also, sir.
So these subjects were all subjected to the same form of exercise?
Yes, sir.
Am I able to believe that?
Yes, sir.
But the exercise wasn't changed. So actually, this is a very small framework that you're really looking at.
Yes, sir. These 25
Very
subjects
narrow,
are maybe means for physiologists, actually the 25 subjects endurance exercise is
I would ask Rishikesh what he believes, because most of us are carrying heart rate HRR on our wrist watches. So there is much larger, huge data which is available.
Sir, unless until you standardize it, it will be difficult to have a meaningful interpretation. For example, the pattern is different in some maximal exercise. The pattern of recovery is different means the pattern of recovery in short term depends upon type of exercise. It also depends upon the intensity of exercise, and it also depends upon in which position you are asking the subject to have recovery, lying down, supine down, legs spread, legs relaxed, legs supported. So all these things influence. They influence autonomic output, so they influence the recovery pattern. So unless until means it's a retrospective analysis, but the data has been taken from a study which was not retrospective in nature.
So Surgeon Commander Arnab.
Sir, can I go back to the last slide? Findings. So I just want to, yeah. So 3 things: one, baroreflex system, reflex system, metabolic reflex, and sympathetic drive. How did you measure objectively 3 things?
In this study or
in this study?
In this study, we have not specifically explicitly measured the baroreflex activity of baroreflex system or gain of the system. We had the recovery data for 2.5 hours. The model was derived based upon the functioning of available literature. For example, literature, there is enough evidences available in the literature that says that baroreflex system responds to the difference between the actual blood pressure. The output also responds to rate of change of blood pressure. The third factor, that is the acceleration or deceleration of blood pressure, I incorporated it from my end. There are evidences that there are biological systems which responds to acceleration, deceleration. For example, vestibular system, the center PPR which controls the eye, and the cerebellum, they respond to acceleration. So it was my intuitive addition that baroreflex system might also respond to higher order changes. The higher the fractions beyond the second order differential equations have been neglected just because it becomes then impossible to solve the solve the equation and get a expression like this. Otherwise, if you incorporate that, means that would have been ideal situation, but if we incorporate that, then we have to use numeric